Video, we talked about the goal of this section is we're going to try to calculate area under curves. And we said that we're going to approximate the area under a curve of something that looks like this with rectangles. So maybe this is doing a good job at approximating the area under the curve with rectangles. In some parts, we're underestimating, like we're missing out on that. In some parts, we're overestimating, like right there, but overall, I think that we can say we're doing a decent job at getting close. But this is one picture. Let's think about how we can do this more systematically. So our goal here, of course, is approximate area by rectangles. Let's say here, this is our function f of x, and I just put on here 1 and 2. Now, suppose that we want to approximate the area under this curve with 4 rectangles. What we're going to do is that we're looking at the interval from 1 to 2. We want to break the interval up into 4 separate subintervals, and we're going to do this at evenly spaced intervals. So 1, 1.25, 1.5, 1.75, and 2. So we have 4 subintervals. So 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, 1.75 to 2. Those are our 4 subintervals. This is a particular case here, 1 to 2, with 4 subintervals. At this point, I think it's worth kind of noting here that we have a general formula, and the textbook presents a general formula for how to determine the endpoints of the subintervals. So suppose that our overall interval is a to b, and we want capital N subintervals. So note that the width here is going to be b minus a. So each of our subintervals is going to have width b minus a over n. So in our case, the case that we just dealt with here, we have width 1. 2 minus 1 is 1, and subinterval width 1, b minus a is 1 over 4. And we can see here each of these intervals does in fact have length 1/4. Now we can also go further and say here what the right endpoints of the intervals are. It's helpful to use notation, say b minus a over n, call that delta x. So the right endpoints are going to be x1 is a plus delta x, x2 is a plus 2 delta x, x3 is a plus 3 delta x, all the way out to x sub n minus 1 is a plus n minus 1 times delta x, and x sub n is a plus n delta x, which is really equal to b here. So in the case that we just worked out here, x1, x2, x3, x4. So the right endpoints, 1.25, 1.5, 1.75, and 2, they can be found by doing 1 plus a quarter, 1 plus 2 times a quarter, 1 plus 3 times a quarter. X of 4, our final one, is 1 plus 4 times 1/4, and that just is going to be our right endpoint B. So first skill that we should be able to do here is that if I give you a given interval, I tell you how many subintervals to divide things into, you need to be able to identify, come up with a list of what are all of the subintervals in questions. Now at this point, now that we've got our subintervals going on, we want to think about how can we use this to actually do this approximation. And so our first approximation method that we're going to talk about, we're going to call R sub n, is the right endpoint approximation. So R for, capital R for right endpoint. We'll talk about other approximations later on. N is the number of subintervals that we're going to divide everything into. And so the method for coming up with this right endpoint approximation is draw a rectangle for each subinterval. And the height is going to be, the height of the rectangle is equal to f of x sub I. So what's going on here is that we're just going to use the value of the function at the right endpoint as the height of the rectangle. Of course, the area is going to be the height, which is f of xi, times the base, and the base is that delta x. So let's just go back to make sure we're on the same page here and draw a picture now. So for this first subinterval, 1 to 1.25, we draw a rectangle with height. So this value right here, this is f of 1.25. Here is a rectangle of height, f of 1.5. Here's a rectangle of height, f of 1.75. And here is a rectangle of height 2. Coincidentally, those two are more or less equal here. But this is what we're doing. This is how we're constructing our first right endpoint approximation. So overall, the area of each of these subintervals is f of xi times delta x, and what we're going to do we need to add up all of these area. So the total area, we're going to add up all of these smaller areas. So it would be f of x1 times delta x plus f of x2 times delta x plus dot 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 f of xn times delta x. We see every single term is going to have a delta x factor in it. So we end up with delta x times f of x1 plus f of x2 plus dot 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 all the way out to f of xn. So this is how we go about constructing a right endpoint approximation. This is a good point, I think, to wrap up this video. We'll do a specific example in the next video. But at this point, here's your first pre-class problem to just write out what are the 6 subintervals. And I'm asking not for the right endpoints, but asking for the left endpoints here of 6 subintervals for the interval from 2 to 5.